In this video, I'll be going over integrals involving exponential functions. So first recall that e to the x is its own derivative. So what that means is d over dx of e to the x is equal to e to the x. Similarly, if we have d dx of e to the ax, where a is some constant, we have e to the x times the derivative of the exponent here. So that's just going to be times a. If we're going with the antiderivative, the similar idea plays out. So if we have the integral of e to the x dx, this is equal to e to the x, and that's because if we take the antiderivative of e to the x, we get e to the x. And then if we have e to the ax, where a is a constant, we get e to the ax, but then we have to divide by a here, and I guess I need to put a constant on both of these. Now this second one, this is what's happening if if we take the derivative of that result, e to the ax over a. If we differentiate that, we're going to have e to the ax over the constant a times the derivative of a times x. So that's just times a. So the a's cancel and we are left with just e to the ax, which is what we have right here. Okay, so if we have a constant in the exponent, we divide by that constant when we're finding the antiderivative. All right, so these are the two general rules for an exponential function that has a base of e. Now let's look at what the rule is when we have an exponential constant where we have some other base besides e. So if we have the integral of a to the x dx, where a is a constant, this is going to be a to the x divided by ln of a plus c. And we can verify that by taking the derivative of a to the x over ln of a, plus c here, but c is a constant, so that'll become 0. So the derivative of a to the x ln of a, well, before we do anything, I'm going to say 1 over ln of a, which is just a constant. Okay, so really we just need to figure out what the derivative of a to the x is. Well, the derivative of a to the x, hang on, how do I want to write this? Let me back up a sec. We can write it like this. So I pulled out 1 over ln of a. So the derivative of a to the x is a to the x times ln of a. So the ln of a's cancel, and we're just left with a to the x, which is what we have right here. Okay, so in summary here, we have the integral of a to the x is a to the x over ln of a plus the constant. All right, so let's look at a couple examples. First, find the antiderivative of e to the negative x. So we'll integrate e to the negative x dx. So this is like we have a negative 1 times x in the exponent. So this is just going to be e to that exponent divided by whatever that coefficient is on the exponent plus c. That's our answer. We could rewrite this as 1 over e to the x, and we could make that whole thing negative. So we could write our answer like that. A second way we could do this is by using a u substitution. If we let u equal negative x, and then du will be negative 1 dx. So if I divide by negative 1, this will be negative du is equal to dx. So we're going to replace dx with negative du. And we're going to have that negative out front in the integral. and then this will be e to the u here. Okay, so e to the u is just, the integral of e to the u is just e to the u. We'll bring down that negative sign, plus c, and then replacing the u with negative x up here. So this will be negative e to the negative x plus c, which is the same thing as negative 1 over e to the x plus c. Okay, so either way we want to do it, we'll end up with the same value here. Okay, let's look at this next one. We have the integral of x squared times e to the negative 2x cubed. So what we notice is that if we take the derivative of this, negative 2x cubed, we're going to end up with something in the form of x squared. So we can do a u substitution here. We'll let u equal negative 2x cubed, and then du will just be negative 6x squared dx. Okay, so we have an x squared right here, and we have a dx. So I can isolate the x squared and dx by dividing both sides by negative 6. Okay, and that's what we'll use as our substitution. So we're going to have the integral. U is negative 2x cubed, so this will be e to the u. And then x squared dx is going to be du over negative 6, and I'm going to bring out the negative 6, or the negative 1/6, I should say. So e to the u, du. So it's really nice when we can end up with an integrand of e to the u, because that will always just end up being e to the u plus c, and then substitute back in whatever we had for u. So this will be negative 1/6 e to the negative 2x cubed plus c. Okay, let's do one last integral here. So in this one we have two terms separated by an addition sign. So what I'm going to do is I'm going to rewrite this as two separate integrals. I need a dx here, plus the integral of 12 dx. This will just make it a little bit easier to calculate two integrals instead of this more complicated expression all at once. Okay, so I'm going to bring out the 7e to the 27x dx plus the integral of 12 dx. Okay, so for this first one, for this first integral, I'm going to have 7 times e to the 27x, and then we divide by whatever the coefficient is on that exponent. And I can write plus c here. And then the second integral, I have the integral of 12 is just 12x. And I could write c again. It makes more sense to write a different constant. But really, it doesn't matter what constant I use, because if I have two constants that are getting added together, I can combine those to be a single constant, right? When we add two constants, we end up with a constant. So I can just write 1 plus c at the very end of whatever my expression is. So this will be 7 over 27 e to the 27x plus 12x plus c, and that's the integral.